Well. Another lesson, trigonometry. So this time, I want to focus on something that we kind of introduced last day, which is the unit circle. And let's get straight into it. So the unit circle, remember, means a circle with a radius of 1 unit, centered at the origin. And the equation for the unit circle is x squared plus y squared equals 1 squared, or just x squared plus y squared equals 1. And that again creates a circle with a radius 1, centered at the origin. Now notice this circle you see here fails the vertical line test. It's not a function. There's times where one input has 2 outputs. And notice your equation, does summarize the whole circle, but it's not solved for y. It's not possible to write the equation of a circle solved for y as a single equation. Because if you do solve for y, you get a plus or minus at some point, which again is actually 2 separate equations. It's not a function. That's it. What if the radius is not 1? Well, if the radius is 2, the equation would be x squared plus y squared equals 2 squared, or 4. If the radius was 5, it would be x squared plus y squared equals 5 squared. To get the idea that if the radius is r, it's x squared plus y squared equals r squared, centered at the origin. A pretty nice simple equation that goes back to the Pythagorean theorem, even though it's kind of a complex idea. And we can kind of see the connection to the Pythagorean theorem if we look right here. If I just imagine this point in red being x comma y, notice if I draw this little triangle here, I have a right triangle. And I can imagine the x coordinate being equivalent to the horizontal distance. I can imagine the y coordinate being equivalent to the vertical height of this triangle. And 1 is the radius. And it's also the hypotenuse of this triangle. And so notice if I think about the Pythagorean theorem, I get x squared plus y squared equals 1 squared, or 1. Right? So you can kind of see how this connects back to the Pythagorean theorem. Again, the equation we have right here of the whole circle is x squared plus y squared equals 1. It's not wrong to put squared there. In some ways I like it because it makes it more clear that that's the radius you can see, but 1 squared is obviously simpler just to say 1. OK, so what I'm going to do next is, for these 2 points, determine which of these are on the unit circle, which means are these coordinates on the actual circle or are they off? And it's actually pretty easy to tell. First, remember that that's your x coordinate, that's your y coordinate. I would start by writing down the equation of the unit circle, x squared plus y squared equals 1. And if these really are coordinates on the unit circle, then I should be able to replace x with -1/2, replace y with 1 over root 2, and the left side should equal the right side. If it is, it's on the unit circle. If not, it's not. And I definitely don't need a calculator for this. And so x squared becomes -1/2 squared, plus y squared becomes 1 over root 2 squared equals 1. And so -1/2 times -1/2 is a positive number. It's positive 1/4. And 1 over root 2 times 1 over root 2 is 1 over root 4, or just 1 over 2, equals 1. And now I can see this is wrong. Right? 1/4 plus 1/2 does not equal 1, which means this is not on the unit circle. If you were to plot that point, it would not be on the circle you see above. So let's look at this point right here. Same idea. X squared plus y squared should equal 1. So in this case, -1/2 squared. Let's see if this equals 1. So again, a half times a half is a quarter, and a negative times a negative is a positive. Root 3 over 2 times itself, well, root 3 times root 3 is root 9, or just 3 whole. And the denominator, 2 times 2 is 4. And now we can see this is true. 1/4 plus 3/4 does equal 1. So this is on the unit circle. As long as you remember that really simple equation, actually, x squared plus y squared equals 1, it's pretty easy to tell if a point is on that circle or not. And that applies to any function or relationship, not just a circle. If a point really is on it, you should be able to substitute the values into the equation, and the equation should hold true. All right. So next, I want to start connecting this back to special triangles. And what I have here are 3 angles shown in standard position. And the one in blue is 30 degrees, the one in red is 45, the one in purple is 60. So for each one of these, I want to determine the exact coordinates of where, for example, a 30-degree angle, and I'll kind of start with this one right here. So this 30-degree angle we see right here, where does that terminal arm cross the unit circle? What are the coordinates of this? Now I can kind of estimate, because I do know this is 1 and this is 1, but I don't want to estimate where that is. I want to know exactly. So how can I figure this out? Well, the key, if I kind of look at this, it's going to get a little bit messy, but I'll draw on this one at a time. So for 30 degrees, let's create a right triangle. And remember 30 degrees is the same as pi over 6 radians. Although in this case, it doesn't really matter what we think about. The hypotenuse of this triangle I just drew, I know must be 1, because that hypotenuse that we see is the same as the radius. And this is a unit circle, so I know that's 1. And so at this point, if I want to find these coordinates, I just need to find the x and y values, or I need to find the horizontal distance and the vertical distance of this triangle. And for that, I can use special triangles again. So let me redraw this triangle down here. But keep in mind, so far I know I have a 30-degree angle, I have a hypotenuse of 1, so I should be able to find x and y. And once I know x and y, I know my coordinates. So let's look right here. Let me redraw this triangle. That was kind of messy. Let's try that again. Ooh, actually, let's see if this works. Ooh, oh, this is exciting. Maybe that's not so exciting. There's no right triangle here. Never mind. I'll just draw this out. OK, so if I have a 30-degree angle here and a 60-degree angle up there, which I don't need to, I'll draw it lightly. Hopefully this sounds familiar. Now, you may, if we think about a special triangle, the most standard 60, 30, 90 special triangle we memorize has a hypotenuse of 2, a shortest side of 1, and a middle side of √3. Well, if I compare that to what I have up here, the only difference is up here my hypotenuse is 1, here my hypotenuse is 2. So I can take this and I can apply it to that if I just have all the measurements I have on this special triangle. So if I just take this and divide all of these by 2, I can apply it directly to that triangle on the unit circle, and I can know exactly those coordinates of x and y. And so literally what I'm going to do is take this, and I'm going to cut all these in half. Divide by 2, divide by 2, divide by 2. And so now I know that the x distance right here must be not √3, it must be √3 over 2. And the y distance right here must be not 1, it's 1/2, because this triangle I'm looking at in the circle is half the size in terms of individual dimensions compared to the one we generally memorize. And so I now know the coordinates of this are, actually I'll just leave it as x comma y right here. It's going to get too messy otherwise. But I now know those coordinates are √3 over 2 for the x and 1/2 for the y. So there's my x coordinate, there's my y coordinate. And so I can say the coordinates would be √3 over 2 comma 1/2. And those are the coordinates of where a 30-degree angle intersects the unit circle. So I can do the same thing for 45 degrees now. So it's going to, right here, I'm going to erase my previous work just so it doesn't get too messy. And so 45 degrees, let's create a little right triangle right here. I'm looking at this angle right here, 45 degrees, or pi over 4. And so again, my hypotenuse is 1. And so one thing you may remember about a 45-degree angle is that means it's also 45 degrees up here, which means these two sides are the same. And we call this a 45, 45, 90 triangle. So let me first show you the most standard way of memorizing it. Although there really are countless ways you could memorize a 45, 45, 90 triangle. But the most common way in my experience is we call the hypotenuse 1, and we call each of these √2. Actually, no, that's not the most common way. That's not wrong. But the most common way, actually, is to call each of these 1 and call this √2. That's it. Teachers may have shown you different things. There's literally countless ways of memorizing it. This is actually the most common way of memorizing this 45, 45, 90 special triangle. And so if I take this special triangle and apply it back to what I have up here, I got to go from √2 to 1. Not as simple as before. If I look at the previous example, I had to go from 2 to 1. Well, to go from 2 to 1, I divided by 2. OK, not quite as simple, but it's actually not far off. Here I want to go from √2 to 1. So √2 divided by what equals 1? Well, √2 divided by √2 equals 1. So if I just take all the measurements of this special triangle I've drawn in red and divide by root 2, I can bring it back to that triangle I've drawn in my unit circle here. So let's take this right here, erase all my highlighting, and let's take all of these and divide by root 2. And so this becomes, this becomes 1 right here. And most importantly, my x-coordinate is 1 over root 2, and my y-coordinate is also 1 over root 2. And so now I know the coordinates of where a 45-degree angle crosses the unit circle. It must be at 1 over root 2, comma 1 over root 2. They're the same thing, which you can kind of tell by looking at the graph I gave you. If I look back up here, if you look at your x and y coordinates, they are both the same. It's not surprising to see they're actually the same coordinate. And then lastly, it leads me to my 60-degree angle, which I can do really quickly because it's kind of the same thing as 30 degrees. If I draw this triangle right here, notice the triangle I just drew is actually identical to the 30-degree triangle that I have right here. Only difference is it's oriented in a different way. But that means it's the 60-degree triangle, for example, in this case, is the base is the shortest side, where the 30 degree is the longest side. But it's the same triangle. It's a 30, 60, 90 triangle. So I don't really need to do all this all over again. All I need to do is realize the coordinates up here must be the same as the coordinates right here, just switched around. If that's not clear, then just literally draw out the special triangle again. But I don't feel like doing that. And so I know the coordinates of this are going to be the exact same coordinates for 30 degrees, but the other way around. So 1/2 over and root 3 over 2 up. And keep in mind, you can kind of see that by looking at it. If I just look at my diagram right here, I can see the x-coordinate actually with a good degree of accuracy. Right? It's halfway between 0 and 1. And if you look at the 30-degree angle, I could see the y-coordinate was halfway between 0 and 1. And so I can pretty quickly jump to that conclusion. And so for today's lesson, you want to memorize all 3 of these. Memorize these coordinates. Literally memorize that 30 degrees goes through root 3 over 2, comma 1/2. 45 degrees go through 1 over root 2, comma 1 over root 2, and 60 degrees is 1/2, comma root 3 over 2. Just memorize those 3 things. It's not much to memorize, and the more you memorize it early on, the easier it makes things later on. Okay, just those 3 things. All right, so now let's move on again. Again, always back to this unit circle. I want to introduce a function that we're just going to look at for a few days, this sort of point theta function. And let me tell you how it works, and then look at a few examples. So this function, the idea is you put in an angle in degrees or radians, and what comes out are the coordinates of the intersection between an angle in standard position and the unit circle. What does that mean? Well, for example, if I replace this theta with 30 degrees, if I find P at 30 degrees, that means I'm asking you what are the coordinates of where an 30-degree angle in standard position crosses the unit circle. Well, that's what I figured out right here. That's the coordinates of where a 30-degree angle crosses the unit circle. And so if I'm asking you what is P at 30 degrees, or if I'm asking you what is P at pi over 6, the answer is what we found about 5 minutes ago. It's an ordered pair, root 3 over 2, comma 1/2. So let's try it for one we haven't done exactly before. What is P at 120 degrees? Which means what are the coordinates of where a 120-degree angle crosses the unit circle? So how can we figure this out? Let's look back up here. First, let's visualize where is 120 degrees. Well, 120 degrees I know is in this quadrant. More specifically, 120 degrees I can see must have a reference angle of 60 degrees. For example, if I look, 120 degrees is, let's say, something like this. If that's 120 degrees, I know that this reference angle right here must be 60 degrees. And why is that important? Because I know, or we just wrote down a few minutes ago, the coordinates of where a 60-degree angle crosses the unit circle. And this here must be the same coordinates, except I can just see that the only difference is my x-coordinate will be negative. But if I just visualize that and compare it to 60 degrees right here, right, they're going to have the same coordinates, just this will have a negative x-coordinate. So that's my sort of rationale as to how I'm going to figure this out. And so now that I visualize that, what are those coordinates? Well, I know it's going to be the same as 60 degrees. And 60 degrees we saw right here was 1/2 comma root 3 over 2. So let me write that down. So this is going to be 1/2 comma root 3 over 2, except in the second quadrant, x coordinates are negative, so it's going to be negative 1/2 comma root 3 over 2. Like everything we're doing, there's not a single complex calculation I'm doing here, but I don't think any of this is easy. All right, so let's look at this next one. P at negative 90. That means where does a negative 90 degree angle cross the unit circle? So let's visualize negative 90. Negative 90 is right here, straight down. So that's a negative 90 degree angle in standard position. It crosses the unit circle right there. So where is that? Well, in this case, that's actually quite pleasant. I can just see the coordinates actually. The x coordinate is 0. The y coordinate is, where is this? It's negative 1. Because remember, this is the unit circle. The radius all the way around is 1. So 0 comma negative 1. That was actually, I think, quite easy once I know what P at negative 90 means. The hard part is not the calculation. The hard part is piecing all these things together. OK, well, that's it for degrees. What about radians? So P at 11 pi over 6. So one option, and it's not a bad option, is to turn this into degrees. If you are going to do that, I would do it like this. First, it's 11 pi over 6. So think to yourself, what is pi over 6 in degrees? Well, pi over 6 is 30 degrees. Well, it's 11 pi over 6, so it's 11 times more. So it's a 30 times 11, which is 330 degrees. So if you're thinking about it like that, it's a good idea to switch it to degrees. If you're thinking about it by applying some formula, how to convert radians to degrees, it's a waste of time, I think. That's it. I haven't done any work. I've just written the question in degrees, which maybe makes it easier. So let's visualize 330 degrees. What does 330 degrees look like? I'll draw it in green. It's almost all the way around, but we stop 30 degrees short of a full rotation. In fact, let me erase my other drawings here, because it's getting kind of messy. OK, so that is 11 pi over 6, or 330 degrees. So what are the coordinates right here? Well, what matters to me really is the reference angle. This reference angle I know is 30 degrees, or pi over 6. And which means I know the coordinates here are going to be the same thing as the coordinates of 30 degrees, but my y coordinate will be negative. And so let's remind ourselves, what were the coordinates of where a 30 degree angle crosses the unit circle? Root 3 over 2 comma 1/2. So let's start with that. So I know this here is going to be, I'll start with root 3 over 2 comma 1/2. That was 30 degrees. I can see this is in the fourth quadrant, so there's a negative there. So there's my answer. Root 3 over 2 comma negative 1/2. Lastly, P at pi over 4. What's pi over 4? Pi over 4 is 45 degrees. And 45 degrees, where does a 45 degree angle cross the unit circle? Hopefully that sounds really familiar, because we literally did that right here. This right here is where a 45 degree angle crosses the unit circle. And so I don't have to do anything else. I can just copy that. 1 comma root 2, sorry, 1 over root 2 comma 1 over root 2. We literally did that a bit ago. OK, so again, this sort of function we'll only see for a few days. It's not terribly important. It's more just kind of to get us an idea about connecting these rotations in standard position with coordinates of where they cross the unit circle. We are connecting a few things together. But again, it always has an angle that comes in and coordinates, an ordered pair that comes out. That leads to my last question. So once again, we have these special triangles here. And so I want to use these to determine all these answers here. OK, so first of all, I want to use this to find the cos of 30. So how can I, again, use a special triangle to find the cosine of 30? Well, I find 30 degrees right here. Cosine is adjacent over hypotenuse. So therefore, the cosine of 30 must be root 3 over 2. I'll make that a little bit neater. What about the sine of 30? Well, to find the sine of 30, I still look at 30 degrees, but the sine of 30 is going to be opposite over hypotenuse, so 1 over 2. And what's p at 30? What does that mean again? That means the coordinates of where a 30-degree angle crosses the unit circle. Well, we did that again, so I just look back in our notes, or look back a few minutes ago, and a 30-degree angle crosses the unit circle at root 3 over 2 comma 1/2. Okay, let's try the same thing for 45 degrees. What's the cosine of 45 degrees? And I'll look here. Cosine is adjacent over hypotenuse, so 1 over root 2. What's the cosine of 45 degrees? Well, cosine is opposite over hypotenuse, so it's the same thing. And where again did a 45-degree angle intersect the unit circle? At 1 over root 2, comma 1 over root 2. And cosine. Cosine of 60 degrees, we can do the same thing. We're going to get 1/2. Sine of 60 degrees, we're going to get root 3 over 2. What was the coordinates of where a 60-degree angle crossed the unit circle? It was 1/2 comma root 3 over 2. So in general, if you want to find the coordinates of where any angle crosses the unit circle, how do we do that? Well, hopefully by now we've noticed that all our cosines were the exact same as the x-coordinate for that angle. All our sines were the exact same as the y-coordinate for all these angles. So how do I summarize this? I can say my x-coordinate is always going to be the same as the cosine of my angle, and the y-coordinate is always going to be the same as the sine of my angle. And that summarizes exactly. And we start to see the connection between these coordinates of points on the unit circle and with trigonometry, sine and cosine. Notice we've had 2 full lessons on, well, 2 full notes here on trigonometry, and sine, cosine, and tangent have barely come up at all. That's going to start changing now. But it's kind of strange. We've had 2 full, pretty big lessons, and very little of it do we actually use so far, sine, cosine, and tangent. That's going to change going forwards. All right. With that said, though, I'm done. I don't think I screwed up too much. I'm pretty proud of myself. Hope you're proud of me, too.